All right, today, chapter 10, we're going to start taking a look at conics, at least for section 10.1. And conics actually comes from the word cone. So this is the image your book has. And this is half of one of the images it's showing on the screen. So conics are created by taking a cone and doing cross sections of a cone. So the first picture, which we won't spend too long, is it's the top half. All right, so when we take a cross section, we cut through the middle, and we look at the two-dimensional object, we get a circle, right? All right, if we cut through it at an angle, we get this shape, and this shape is an ellipse, right? So it's circular-ish, but it has this sort of flat on one side and elongated on the other. If we cut through it at an angle a little bit more drastic, where it actually hits the bottom of the cone instead of cutting through the entire side of the cone, you get this shape, and this shape's the parabola. Okay? The last one, I don't have the top half of this thing, if you were to have the top half of it. But if you can imagine taking our cone and you were cutting down straight, like vertically, and you're cutting down and you had this half of the cone and the top half of the cone, we would end up with the shape over here on the side. I can get it off. And this piece, along with the top piece up here, would create a hyperbola. And you've probably seen all three of those shapes, four of those shapes, if you count the circle as uniquely different, before. But you may not have known where they came from. And they come from cross sections of a cone. And that's why they're called conics. So this whole section, we're going to be taking a look at conics, and probably from a perspective that isn't the one you did in possibly an Algebra 2 course, or maybe a pre-calc course. College algebra. Yeah, college algebra and Algebra 2 are the same thing, just so you know. They mimic one another.
Why don't we get college credit for taking Algebra 2 then?
Because people who take college algebra are very fortunate to get college credit for it. That's why. All right. Theorem 10.1 is where we're going to start, and we're going to start by taking a look at one of these conics. The first conic we're going to actually take a look at is the parabola. So we're not looking at a circle. A circle is really just a specialized case of an ellipse. So everything we look at when we look at an ellipse could apply to a circle, and I'll tell you how when we get there, but that's why we're skipping over that one, is because it's really just a specialized ellipse. All right, so Theorem 10.1 says the following. The standard form of the equation of a parabola with vertex HK and Directrix. We'll talk about what that is in a minute. Y equals K minus P. The K's are the same thing in the vertex form and in the Directrix form. And we'll talk about what P is in a moment too, is the following. So the first one is X minus H squared equals 4P times Y minus K. And if we have this one, this is a vertical axis. And if you want a reminder, it means that it opens up and down, up or down. That's what it means to have a vertical axis. And there's another form of a parabola as well. So in this one, it opens up and down. So what other direction could it potentially be opening?
Left, right.
Yeah, left or right. And so if it opens up and down, we have the one that you're most familiar with from college algebra, right? Where it has the x squared, and you can see it in this formula. But if we're working with it opening left or right, while it's not a function, it is a parabola, and it has this very similar form, but y is going to be squared instead of the x being squared. So for the Directrix, again, I promise I'm going to show you what a Directrix is, but for the Directrix, x equals h minus p, the equation is And so instead of x minus h, we have y minus k being squared. And then on the other side, we have that 4p still, but now it's times x minus h. And this is a horizontal axis. And just like we talked about, it's opening left or right. Okay, I'm going to shrink my picture so that, well, maybe I am. It's not going to let me move my picture once I've pasted it on there. It might not. Okay, I'll shrink my words instead. I want to draw a picture, and I want to draw on this page since I've got all the language right here with it. So you guys all have it written down. We'll just shift it up. All right, so there's two different parabolas we're going to draw. The first one will be the first one listed, the one that we are most familiar with. And I shouldn't draw it quite like that. I'll draw it dotted because it doesn't have to be in any particular location. Actually, you know what? I'll take it back. I'll draw it like this. All right, so here's my H, and here's my K. Of course, they could be in any quadrant. So the vertex is happening right there at the HK. Because it's a vertical one, it's either going to open up or down. And you know how to do it with a standard form of a parabola that's given in a college algebra course, right? What happens is that if your squared term is negative, it opens up, right? If x squared is negative, it opens up, and if it's positive, it opens down. I just said it wrong. If it's positive, it opens up, and if it's negative, it opens down. There we go. And you might look at this and say, well, yeah, but it doesn't look like that. It doesn't look like the formula that I have seen before. And that's true. But if you can imagine, this piece right here is, I could separate it so that I can make y equals. I could actually move, let me do this piece first. I could move this to the other side with division, right? So that it was grouped over there with the squared term, and then I could add the k to the other side. So the value that would end up being multiplied by the x squared term is going to be the reciprocal of the 4p. 4 is positive, so it's p itself that's determining whether it opens up or down. So in particular, if p is positive, it will open up. And if p is negative, it will open down. So feel free to jot that down if you would like. So p positive, it opens up, and p is negative, it opens down. And we'll do the same thing descriptively with our horizontal axis one in a moment. So I'm just going to choose to let it to open upwards arbitrarily at this point and go like that. All right, so the focus and the directrix. Well, the focus and the directrix actually talk about how wide or how narrow the parabola is. If the focus and the directrix are far away from the vertex, it's going to be a very narrow parabola, and if they're very close to the vertex, it's going to be a very wide parabola. Now, for the purposes of what we're doing, we're not worried too much about drawing the wideness or the narrowness. We're simply going to be drawing the focus and the directrix part that we're finding, okay? So in terms of our picture, the way that it works is this. The focus is on the inside of the parabola, and it's a distance, hang on, let me draw it over here so I'm not cluttering things up, of p away. So if the parabola opens upward, the focus is on the inside and it's above the vertex. And if the parabola were opening downward, it would be on the inside. It would be underneath or beneath the vertex. And the directrix is equidistant on the other side. So down to here-ish, and I'll do it in red. And the directrix is not a part of the graph, just like the focus isn't. It's a part of creating the width of it. So I'm going to draw it in kind of like we would do with an asymptote, where you draw it in dotted. And that would be my directrix. And if you take a look back at the equations that it gives you, for the directrix right here, the directrix for this one is the k value, and it's minus p, right? And the directrix would be the focus would actually be the same. I haven't written those down yet. That's actually the next thing on my piece of information to write down. The focus would be the same x value, and I would add p to it. So the focus lies on the axis. So what do I mean by axis? Well, I mean the piece that cuts the parabola in half. That's my axis. It lies on the axis, p units from the vertex. And its coordinates go like this. So if I have that vertical axis one, the x value stays the same. And you notice we take the y value, which is k, and we add p to it. Right? And if p is positive, then it will be adding p in a positive sense. That means it goes above. If p were negative, it would be actually like subtracting a value because p is negative, and it would be below. And this happens for, like I said, the vertical axis. And if we're working with the horizontal axis, it's the x value that gets adjusted. So it's h plus p, and the k for the y value stays the same. So let me draw, I think there's enough space there down in the corner, barely maybe. The other one that we were referencing to go opening left and right. So opening left and right, I won't bother to put the h and k in, but let me just sketch the imagery that we get. So you have, we'll open to the right. We would have a focus in the interior. It's always on the interior of the parabola. And that distance away is p. We would go a distance of p in the other direction to get our Directrix. Put in there. It looks something like that. That was very light. A little bit darker. How about that? So there's my Directrix on the outer component. In particular, the Directrix is never going to cross through the graph, so that's why it's happening on the outside as well. And that's our focus on our Directrix. Okay, I mentioned that if p is positive and I've got a vertical and it opens up, if p is negative and I've got that vertical and it opens down, what do you think would happen if p is positive and I've got a horizontal axis like this last picture I drew? Do you think it would open to the right or to the left? Right, and it does. It happens just like we would expect. So on the second one that we just wrote down, if p is positive, it opens right. That's the one I've drawn, and that's why I drew it, so that it would mimic the same one I already drew. And if p is negative, it opens left. And you should see that that makes sense with my description here for my focus, right? I add p to my hk value right here. That moves me to the right. Okay, any questions on that? Yeah, Hannah.
Is the Directrix, is that like supposed to be a line, or is that like...
It's a line. I'm trying to draw it as a dotted line, and that dotted tool looks more like real dots, not like dashes. We usually draw them kind of dashes when we draw them. But yeah, it's a dashed or dotted line. Yeah. Anything else? We're going to do an example. Okay, let's do an example. So our first example for today, whoops, let's use black. Wants us to find the vertex, focus, and directrix of the parabola. And it wants us to sketch it. So the first one that we're going to do together is going to already be in a kind of nice form to start with. So I have 4 times x plus 2 minus y minus 1 squared and it's going to equal negative 4. Okay, so it's partially factored, which is why I said it's kind of in a nice form already. I do want it to really mimic one of these designs over here, though. Not designs, but formula structures. Which of the two is it going to mimic? The first one or the second one?
Second one.
Yeah, the second one, because the y is squared. So I want the y squared piece to be on one side, and I want everything else to be on the other side. Is everybody good with that? Okay. So the y squared piece, I'm actually going to move it over here, and I'll move my 4 over here. Now it's going to be written backwards from my other screen. That's not a problem. We can switch it if it bothers you. I have 4 times x plus 2, and then I have plus 4 now, and it equals y minus 1 squared. I just chose to do that because then I would have the positive in front of the y minus 1. The left-hand side, however, is really not quite in the form that I want. I want there to be some factor in front, and then I want it to say x minus a number. So I want to simplify this by cleaning it up and then refactoring. So if I multiply this out, I have 4x plus 8, and then I have plus 4, which is 4x plus 12. And my goal is to have the x be linear inside my parentheses. So not linear, but have a coefficient of 1 is what I meant to say. So I can pull the 4 out, so I have a coefficient of 1 in front of my x, and then this will be a 3. So I'll always be able to pull a 4 out of it. It doesn't necessarily mean that the 3 that I got here will end up being a whole number. Or I could end up with a fraction there. And then my other side is the y minus 1 squared. All right, so in this case, what is p? It's 1. P is 1. So if you like formulas and you want to be able to go back to here and say, okay, I'm going to use these formulas, this y equals k minus p, and this h and then k plus p for my focus, you can do that. But you can also do it from a more visual perspective if you'd like by drawing the pieces of the graph and reasoning through it. I do things very visually. That's how my brain works, but you can do whatever you'd like. Somewhere along the way, you're going to have to graph it. So I'm going to graph at least the pieces we know for the moment. So at the moment, we know that we have a vertex at a specific spot. Of course, we haven't written it out, so maybe we should start there. What is the vertex for the equation that I've got? And I'm specifically looking at this point now of my equation. Negative 3, 1. So the order is always xy, just like it always is, but it's the x value is grouped with the x, whether it's on the right side or the left side doesn't matter, and then the y value has the k value with it. Okay, so negative 3, 1. So over here on my graph, in fact, we're going to do that. We're going to switch to some graph paper. We have negative 3 and 1. So here's my vertex. How nice is that graph paper? Don't you wish you could do that on your paper? Just turn it on, right? Yeah. Annika's like, I'm already doing it on graph paper. Yeah, okay. All right, so here's my vertex. That's good. And is it going to open up or down? Up. How do you know? P is positive. Yeah, it could be right or left. Oh, I'm sorry. I was getting distracted. Or right or left. So it should be right. Thank you. I've even got it on my picture staring at me. It'll open to the right. Yeah, cool. So it opens to the right. And that dot that I used for my vertex tells me that I'm going to use that as my center, if you will, and move to the right and to the left to create the focus in the directrix. So I'll move to the right for the focus because it's going to be inside of my parabola. So what's my focus? Negative 2, 1. And I'm going to move 1 to the left for my directrix. Now, please be careful, and we're not just going to write down the directrix as negative 4. That's not what the directrix is. The directrix is a line. What is the equation of that line? It's x equals negative 4. So the directrix is always going to be either x equals or y equals, and of course that depends on whether it's a vertical or a horizontal line. All good? Now, this one was kind of nice because it was already in that semi-factored form. It almost had the pieces in the right places and so forth. We didn't have to do very much manipulation. We will sometimes have to do some manipulation. I'll do an example later on within another form of a conic so you can see how that works. All right, let's take a look at another one of our conics. So ignoring the circle, the first one we did was parabola. The second one is actually an ellipse in terms of that diagram that we saw. So Theorem 10.3 is the standard equation of an ellipse. You might notice that we skipped Theorem 10.2. 10.2 is about symmetry in terms of a parabola. We have a pretty good idea when we're looking at our parabola about symmetry, so we're going to move past that and assume that that piece is not super important for us to hit upon since we've seen those pieces before. So this one talks about the standard form of an ellipse with center HK and major and minor axis of lengths 2A and 2B. What I'm about to show you as well is going to look a little bit different if you go and compare what I'm doing to the book. They give you two equations. They give you an equation that talks about what if the ellipse looks like long vertically and what if it looks long horizontally. I'm collapsing these into a single equation with a slightly different definition. So if you're going back to look for something that's not matching up, that's going to be why. So here's the basic form, or the standard form. It's x minus h squared over a squared plus y minus k squared over b squared equals 1. And this is the part that allows me to do this, is that I make this disclaimer. Whichever of a squared or b squared is larger determines the major axis. Now we don't have a focus. We do have a center of our ellipse. Maybe I should even write that down. I don't think I wrote it in before. Oh, I did. Center HK. It's written up here. So I do have a center HK. Instead of having a focus, I actually have foci. So there's two of them. So the foci lie on the major axis C units from the center. And so what is C? Well, this is happening where, again, this is a difference a little bit from your book. It's where C equals the absolute value of a squared minus b squared. It's really just the difference in the denominators squared, the denominators which are squared values. And I just take the larger value minus the smaller one. In case you decided to do smaller minus larger, as long as we stick those absolute values on there, we're good to go. It's going to be the same quantity. All right, so some pictures. I won't draw them on an axis because they aren't necessary to do so. I can label them without. So here is that sort of horizontal ellipse. It will have a center, of course, approximately right there. The way that this is drawn, the major axis is the longer axis. You can see it visually without question. So our major axis here is this one right here. So this is my major axis. We could cut it in half vertically, and that would create our minor axis. Of course, that dot that I put in the middle, that was my center. It's HK, the center. And there are dots. I'll change the color just because I've got a lot going on in this graph already. Let's try for a blue. And I'm eyeballing this. These are found specifically, but visually speaking, they're equidistant away from the center at a length of C. So this length right here is C to get out there. And these are my foci. And if I just took the same picture and I tilted it, right, 90 degrees, I'd have the other image. All right, the major axis would be the vertical one, and the minor axis would be the horizontal one. And now my foci would go slightly above and slightly below. And there are equations in the book, much like there were equations over here for the focus and the directrix on this one, for finding the foci, for finding the major and minor axis and all of that. But again, it's easier to just do it with the graph as you're going. So that's how I'm going to show you to do that. But if you don't like that and you want to use the equations, by all means, go find them. There's one other piece of information that's important about ellipses. And this is something called the eccentricity. And I think I have space enough to write it here, so we shall. The eccentricity is the measure of the ovalness, and yes, that's a real word, ovalness of an ellipse. And it's found by the equation E, so E is for eccentricity, and it equals C over A. The C here is the distance from the center. It's the same C we talked about before. The A is actually talking about the major axis. So if you prefer not to write A and you want to actually put major axis, because sometimes my A and my B are going to switch letters, that's fine. I'm going to leave it that way just because that's where our book leaves it, though they've defined it slightly differently. So where C is the distance from center to foci, and A is half the length of the major axis. Sorry, that's crammed in there at the bottom. I hope you can still read that. Okay, so, I mean, because obviously there's some measure of how oval my graph is. So there's some pieces that would look, whoops, almost circular like that, right? It's not quite a circle. It's slightly vertical, but I could also make it really narrow. I'm off the screen so much, right? The eccentricity is what measures how oval the graph is. So we're going to do an example. And it's going to feel, the directions are going to feel very much like the parabola one that we did. We're identifying a bunch of pieces and we're sketching it. So we're going to find the center, foci, vertices. I did not identify those. I'll do that in a minute. Vertices. And eccentricity. Of the ellipse and sketch the graph. So I'm going to flip back over, identify our vertices for us. Our vertices are actually the corners of the major axis. So they're here and here. So this one and this one are our vertices. You might be asking, well, is there a name for the ones that go along the minor axis? And some books that I've seen do call them the co-vertices, but they're not the vertices. The vertices are just on the corners of the major axis. And that's all that we're asked to find. So, and then the last piece over here, after we do this, sketch the graph, is actually what we will be doing along the way to make it easier on ourselves. And the example that we're going to start with is going to look messier than the last one that we did, in the sense that it doesn't have any factoring happening yet at all. So x squared minus 4x plus 9y squared equals 5. Before I continue, I'd like to point out that there is a portion of your homework that's actually going to ask you to simply look at equations and say, what's an equation of? And we should be able to do that based on what we know about these three different types of conics. We haven't got to the third one yet, of course. But what about this equation makes it an ellipse, whereas the equation over here made it a parabola?
You're adding both x squared and y squared.
Right. So in the the parabola one, we only have one of our variables that's squared in the problem, right? Our example here, it was y squared. But when we're doing an ellipse, we have both of them squared. Now, a hyperbola has both of them squared as well. The difference between the ellipse and the hyperbola is that in an ellipse, they're both positive, or at least both the same sign. They can be both made to be positive. So you notice the x squared is positive and the 9y squared is positive. That's what's going to make this an ellipse. If that had a negative 9y squared instead of a positive 9y squared, I would not have an ellipse. I would have a hyperbola, which we'll see an example of that later. Okay, so we're about to do a process that you are familiar with, but you might not have done it in a while, and it's called completing the square. Okay? The first time you saw it was probably in an Algebra 2 course in high school. Maybe in a college algebra course you revisited it, maybe not. But in order to do completing the square, we want to group everything with one variable together. And so there's actually only x's that have two locations. The 9 is 9y squared, and there's no other y's. But on the x squared, we're going to rewrite it, and I'm going to leave a little bit of space after it before I write the other parts of the equation. So what I want to do is I want to write in this place the completing the square value, and I'm always completing the square in the same way. I take the linear term of the x, which is technically negative 4, but 4 is fine, and I divide by 2, and I square it. So what is negative 4 divided by 2 squared?
4.
It's 4. And if I add 4 to the left, I have to add 4 to the right. Now, a little bit of a reminder of some sneaky things that crop up when you're doing these. If for some reason I had, say, 4x squared minus 8x like this, and I wanted to complete the square, I do not take negative 8. I need the coefficient in front of x squared to be 1 before I'm able to complete the square. So the first thing I'd need to do is I'd need to factor the 4 out like this. And then I'd be using the negative 2. So negative 2 divided by 2 squared would actually give me the number 1. But I didn't add 1 to my equation. What did I really add? 4. The 1 is multiplied by 4. So to compensate for adding 4 to this side of the equation, I will balance it by adding 4 to the other side of the equation. And you might say, well, could we actually subtract the 4 from the side we're on? You could. It's just that I want my constants on the other side anyway, so I might as well compensate by doing the addition to the other side. Okay, so that's one of those things that sneak up when you're doing completing the square that we sometimes forget about. Back to our problem. The reason that we want to complete the square is because it will factor as perfect square trinomial. So perfect square trinomial means that I have the first piece, x squared, square rooted, so it's x. I have the last piece 4, square rooted, which is 2. And I have the sign that's on the middle value, a negative. And all of this is squared. The other pieces, I've got 9y squared. And now on the right-hand side, I actually have 9. And we're getting very close to the form that we want. Can you look at the form that we want and tell me what it is that we still haven't done, or how it differs?
It's not all equal to 1.
It's not all equal to 1. Yeah, I need it on the other side to say equal to 1. Now, that may or may not mean that I actually have denominators. In the picture here, it looks like they have got an a squared and a b squared. Technically, a or b could be 1, and they wouldn't look like they had denominators. But that comes about, and you'll see happen very quickly, because I have to divide by 9. So I need this to be a 1 on the right-hand side to truly be in the ellipse form. So on the left-hand side, I have x minus 2 squared over 9. And on this one, I really have y squared, just y squared. But it might be helpful to write it instead as y squared over 1. If you don't write it that way, it's okay, but just in terms of observing the other features. And then this equals 1. Now, we could have had to do the same thing for y, right? If it said y squared minus 2y, we would have had to complete the square twice in this problem. So we did one that just had 1 completing the square, but it is possible that we could have 2. Okay, let's start with the center. What is the center of this one? 2, 0, you got it. So there's no number grouping with the y, so it's an understood 0, so it is 2, 0. What is my major axis? First of all, is my major axis horizontal or vertical? It's horizontal. I have a horizontal vertical axis. How do you know, Aaron?
Because the x is going to be like more stretched out than the y.
Yeah, so in particular, the bigger number is underneath x, right? Yeah, the bigger number is underneath x. It's actually a 9 compared to the other one being a 1. You were actually answering for me how far away I need to go. So let's actually draw the picture and put those pieces in it as we go. And we will switch to a graph as well. Okay, so my center is at 2, 0. So I'll start by putting the center on my graph. So 2, 0 places me right here. Okay? So again, there's lots of equations, and if you want to go through and use the equations that are in the book to find the foci and the major axis and minor, you can do that. But you can also do it just with the pieces that are present on the equation. So you told me 3. So will I go 3 left and right, Caleb, or will I go 3 up and down?
Up and down.
Nope.
Option right.
Why?
It's horizontal.
Yeah, because it's horizontal. So the number underneath the x squared component, when I square root it, right, because this is really 3 squared and this one is 1 squared, the 3 tells me I go left and right 3, and it's underneath the x. So that actually tells me which way I go. It's the x direction. So I will go 3 to the left and 3 to the right, like so. And then the number under the y tells me how far up and down I go. That doesn't give me vertices, but it does help me to be able to graph this in a moment. So I have these 2 pieces. So I don't have them written down yet, but I certainly can. What are my vertices? Good. -1, 0, and 5, 0. So in terms of directions, we have found the center, we've found the vertices, and we're in the process of sketching. So we actually have enough information at this point to create the sketch, if you would like. We'll see how well I can do. I'll shift it. Not too bad. This would be my ellipse. Let's find the foci next. And so my foci, finding c squared, means that I take the larger value of the denominators, which is 9, minus the smaller one, which is 1. So it's 8. C squared equals 8, and if I square root, we're looking at distances, so I don't need to worry about positives or negatives. It will simply be a positive because I'm talking distance. What is a different way of writing square root of 8? Yep. We will simplify, or at least reduce it as much as we can underneath the radical. It is 2 square root of 2. Now, 2 square root of 2 actually tells me that's how far away from the center I go in each direction. In terms of graphing, it would be nice to know approximately what 2 square root of 2 is. Can somebody find that for us? Grab your calculator. Hannah's got it, I think. 2.8-ish. Does that sound okay? almost 3. Okay, so in my picture, I can plot those now. I'll change the color since I've got red going on. So 2.8 puts me about right here on the left or I'm sorry, on the right and then on the left. Those are my foci. The foci are closer to the point in the middle when the circle is less, I'm sorry, when the ellipse is less oval, more circular, in other words. All right, finding the foci, though, means that I would take the center point and I would add and subtract the 2 square root of 2. So my center, which was negative 2, I'm sorry, not negative 2, 2, will be 2 plus 2 square root of 2, and it's 0. And 2 minus 2 square root of 2, 0. And these are my foci. Okay, the thing we haven't found yet is the eccentricity. So eccentricity, that's E. E is a ratio of C, that's what we just found, 2 square root of 2, over half the length of the major axis. So we didn't actually talk about the actual length. What's the length of my major axis?
6.
It's actually 6. So the length goes clear from one vertex to the other one. But half the length was the same value we got for A. In this problem, we called it A even. And it was 3. Yeah? So the eccentricity is 2 square root of 2 over 3. Quite eccentric. That's right. Okay. We don't have time to do an example of the next one, but we do have time to write down the definition. So we'll write down the definition, and we will table this section, and it'll be due on Monday instead of on Friday. And I'll give you the homework, too, if you wanted to start on it, just so that you have that. But let's write down the definition of the last type of conic, which is a hyperbola. So this is Theorem 10.5, and it's the standard equation of a hyperbola. I cannot collapse these into one like I did with the ellipse, so this one actually looks just like your book. So the standard form of the equation of a hyperbola with center HK is the following. So there's 2 of them. One of them is x minus h squared over a squared minus y minus k squared over b squared. And it's equal to 1, much like with my ellipse. This one has a transverse axis that's horizontal. The other form flips those 2 fractions, which is necessarily different because I don't have addition this time, it's subtraction. So I have y minus k squared over a squared minus x minus h squared over b squared equals 1. And when I do this, the transverse axis is what? Yeah. Transverse axis is vertical. The vertices are A units from the center foci are C units from the center. But here the C or c squared specifically, is actually a squared plus b squared, and we add them. So I'll draw a picture of this next time, but you have those in your notes already. And let me write the homework on the screen just so that you have it. It's going to look like quite a lot. And in some regards, it is quite a few problems. But there's really only 2 of each type, and we just have a lot of types of things we're doing. So this is page 696. It's problems 12, 13, 19, 22, 26, 27, 31, 34, 37, 40, 41, 44, and then this 51 through 56 is just an identification. You're looking at them and saying, it's an ellipse, it's a hyperbola, it's a parabola. That's all you're doing in the last set. So if you'd like to start looking at that, anything that doesn't involve hyperbolas, you are set to go and work on. You also have test redo that you're working on. So take a look at both of those things, and we will pick up with the rest of the part about the hyperbola next class period.